Alright, so in this video I want to talk a little bit more about the second derivative. Okay, we've talked about the first derivative in association with graph. We've talked about how the first derivative is the slope. I want to talk a little bit about the second derivative and how that then relates to the graph. We've talked a little bit about some of this as we've gone through some other problems and videos, but I want to go into just a little bit more detail. It'll give us a little bit more understanding about these functions and their graphs. Okay, so let's consider the function x to the fourth minus 4x cubed plus 5. Okay, now if I were to find the first derivative, then what I would get is 4x cubed minus 12x squared. Okay, now of course from that I could find my intercepts. I could create a sign diagram. If I take out x squared, then I'm left with 4x minus 12. And so at 0 and at, add the 12 divided by 4 at 3, I'm going to end up with places where the derivative, so if I'm doing a derivative sign diagram, that's where my values will change. Let's see, if I put in, say, a 1, then I'll get 4 minus 12, so that's negative, so 1 is negative. Note that 0 is double, so it needs to not alternate, and then across the 3 will alternate. So I've got a graph that goes down, flattens out, goes down, and then goes up. Now let's go just a little bit further, and we'll look now at the second derivative. And so if I look at the second derivative, I'm going to get f double prime of x equals 12x squared minus 24x. And so again, I can go ahead and factor out maybe a 12x, and I get x minus 2. So for the second derivative, if I do a sign diagram, I got 0. This time it will alternate. It's only a single root there. And then I add 2. And so, again, put in 1. I'll have 12 minus 24, so negative, and then positive on either side. Now, we know that the places where the first derivative is 0 is called the stationary points. The places where the second derivative is 0 are called inflection points. Okay, now inflection points are places where the concavity changes. Okay, it's where we can change, and concavity is, in the last video I was talking about, an up parabola or a down parabola. Now the significance of this is, look at this u, your positive parabola, and we're not talking specifically about parabolas, but just the general shape. Note that as I go to the right, okay, here I'm decreasing and there I'm increasing, but look at the slope. The slope here is very negative, and as I move through my graph, my slope is always increasing. And because the slope is always increasing, we say that it is concave up, or it has positive concavity. Okay, note on this one, the upside down parabola, upside down u, that I have a very positive slope here on the left hand side, and as I progress, what happens to my slope? It goes more and more negative, steeper and steeper negative. And so that's what we call concave down, or a negative concavity. So when we look at the second derivative, at this 0 point, it's going to be changing its concavity. Here it's going to be concave up. At the negative, it's going to be concave down. And then here it'll be concave up again. So if I look at before the 0, it says it has a negative slope and it's concave up. So we look at our graph, and this first part right here, the left-hand side, is a negative slope, and yet it's concave up. So my graph would look something like this. Okay, now it's got to flatten out at 0. It doesn't have to cross the x-axis there, but it does have to flatten out because that's what a stationary point is. Now after 0, it says it has a negative slope and a negative concavity. And so looking at my negative concavity here, a negative slope would be the right-hand side right here. So that's a negative slope, negative concavity. So after this, it's going to go down. Now, at 2, so my next point, I see something here at 3, another stationary point at 3, but at 2, it changes concavity again. It changes from this slope downwards to having a positive concavity. So it's a positive concavity, but between 2 and 3, it's still a negative slope. So positive concavity, negative slope would be the left-hand side again. And so it's going to look like your upwards U right here. Okay, so we had, this was negative slope, positive concavity. This was negative slope, negative concavity up until the 2. And then I've got a negative slope, positive concavity. At 3 it has to flatten out because that's a stationary point. And then after that it goes positive again. So it's a positive slope, positive concavity. And so looking at my concavity, the U shape, upwards U, then it would be the right-hand side. So we go the right-hand side just like that, and that would finish off my graph. And so we can kind of put some more pieces together. We can figure out exactly where it's changing its concavity by using the second derivative. We'll note that this 0 is actually a horizontal inflection because it's a stationary point, but it's also an inflection point. Okay? Now, this is what the graph actually looks like, and we can see that. Before the 0, we've got concave up, and yet it's a negative slope. From 0 until 2, it's a negative slope and concave down. Then after the 2, I've still got a negative slope, but now it's concave up because I've got the left-hand side of that curve there. And then at 3, it now curves back up just like that, which matches our graph. All right. Note here that it does have an inflection. It changes concavity from a positive concavity to a negative concavity, but it's also a stationary point. It's horizontal. Okay, so let's look at another example. You know what? That's the one we just looked at, so we already did that. Awesome. What I want to do with that now is say, okay, let's sketch f prime and f prime of double prime of x on the same graph. So I've got this graph here, which is f of x. We want to be able to create the f prime, the first derivative graph. Now, in order to do that, what we're going to need to do is consider the pieces. You know, if we look at this, we say that looks generally like an x to the fourth. So f of x could possibly be an x to the fourth. So what do we expect? It's at least it has an even power. What do we expect the f prime to look like? Well, we then expect f prime, if we bring the power forward and subtract 1 from the coefficient, the f prime of x should be something of the order x to the third or some other odd order, right? Depending on if this is a double or triple or whatever, you know, whatever could be happening. So anyway, what we're going to do is kind of look at this and say, well, let's see if we can figure out what this should look like. Well, I know that the derivative graph has a value of 0. The derivative value equals 0 when? At a stationary point. So I'm going to look through my graph here and I'm going to find the stationary points. Here's one, right? The graph is flat, slope of 0. And here's one. Graph is flat, slope of 0. So the derivative graph needs to have a value of 0 there and also here. So there's my derivative graph. Okay? Now, from there, we're not going to have exact values. We're just going to kind of sketch it. But notice that before this one, it's a negative slope. Now, if it's a negative slope, that means that the derivative graph has to be below 0. So it's going to come up here. Something like this. So I get to the point. Now, after that slope, after that point, notice that the slope is still negative. Okay, so we're going to go down like this. Go down. All right. Now, at this point, it's negative, 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 which means that the value needs to be negative. But at this point, it's back to 0. So I got to be able to get back up to 0 by the time I get there. So I get back to 0. And then after this, note that the slope is positive, positive, positive. And so I continue with a positive slope. And note that that does look roughly like a cubic function. Now, one thing of note, if I can figure out where the concavity changes, if I can see, okay, well, this is all concave down, probably to about there, then here is approximately concave up. So at this point, it's changing concavity. Now, if it's changing concavity there, that needs to be a maximum or minimum for my graph. And note that I did pretty good. I'm probably going to change it just a little bit so I make sure that I got my minimum there at that point before it goes back up again. Note here that that was already taken care of. It's changing from a positive concavity to a negative concavity. So at that change of concavity, I already had a minimum or maximum for my derivative graph. Okay, well, let's go on and do the second derivative now. Second derivative, well, should be, if I bring the 3 forward, it should become something like a quadratic or some other even-powered function, just like that. So we can do the same thing. We can do exactly the same thing that we just did. We can look at the maximums and minimums here, find where you have stationary points. I'm going to ignore the original graph for just a minute. I'm just going to look at the derivative graph. So I'm looking at my red graph. The second derivative is the derivative of that. So if I consider the red graph to be my original function, then I've got a stationary point here, and I've got a stationary point down there. So those should be the x-intercepts for my second derivative graph. Now here, notice I have a positive slope, negative slope, positive slope. So I need to have positive values here, negative values in between, until I get there, and then it's a positive slope again. So I can create the second derivative graph using exactly the same process that I used to create the first derivative. Now, being the second derivative, it should also match up with the original graph. Note that here I've got a positive concavity up until this point right here, 0. So that's why my second derivative has a positive value. After this point, I've got a negative concavity until approximately this point right here. The negative concavity is a negative second derivative then. At this point, point of inflection, that's why it's at 0, and then it becomes concave up. And because it's concave up, that then leads to a positive second derivative, which is what I have there. And so even though I can create this green graph, the second derivative, from the first derivative, I also want to make sure that it matches the information from the original graph here. Okay, so hopefully that gives you an idea of how we can use these principles, these concepts from derivatives, to draw the graph and to estimate what the derivative and second derivative graphs should look like. All right, go ahead, try this one on your own, and then I'll work it out. Okay, so hopefully you paused and worked through it. This one is a little bit different because this gives us a graph of f prime of x and asks for f of x. Okay, well, you'll remember before on that previous screen, when I was looking for f prime, I found the stationary points, and I said that's where f prime was 0. So if I move forward, if I found stationary points on f of x, then that meant that the derivative was 0. Okay, well, now I'm just going to find where the derivative is 0, and those are going to be my stationary points for f of x. Now, this being the derivative graph, right here, I've got negative values. What do negative values for a derivative mean? It means you have a negative slope. Between these 2 points, I've got positive values. Positive values for the derivative mean a positive slope. Here I've got negative values again, and then on to positive values. Okay, so negative slope, positive slope, negative slope, positive slope. Now this looks like it could be some type of cubic, though don't restrict yourself. It could be a quintic or something else. But general shape, odd powered function. Notice I'm not saying odd function or even function, it's an odd powered function. And so we can use this information and say, well, if that's f prime, then f of x should be some type of x to the 4th. So let's go ahead. I'm going to pull up my red pen again just because it shows up a little bit better. And if this is a stationary, I don't know where this occurs. Actually, where it occurs doesn't matter. All I know is that it has to be stationary somewhere. So I'm just going to say, okay, let's just make it stationary here. Remember, when you take a derivative, you lose the constant from the f of x. So if this was x to the 4th plus 3, you lose that plus 3, and that plus 3 is your vertical transformation. And so that's gone. If all you have is the derivative, you can't find the exact f of x. That's why it states one possible f of x. But here, I do need a stationary point. It has a negative slope before and a positive slope after. So that means it needs to have a negative slope before and a positive slope afterwards. until I get here to -1, at which point it needs to be stationary again. So we'll go up, and then, oh, it looks like I lost my stationary again, so it's going to go up to that stationary point. Okay, and it's going to flatten out there. And then here, notice that I have a negative slope. So I'll go negative slope again until I get to 1. So negative slope would look something like this. And then after that, I should have a positive slope again, which means it'll go up. And notice that that gave me a very, maybe not nice looking, but a good, possibly quartic or some other even function. Now, one thing that I do want to check is I want to compare this with my second derivative. Okay, so remember the second derivative has a value of 0 when I have a maximum or minimum for my first derivative. Okay, so at these 2 points there should be an inflection point. Okay, so these two should be inflection points. So right there, looks like I'm going from concave up to concave down. And then again, at this point where I've got a minimum, so the derivative is 0 there, therefore the second derivative is 0 there because there's no slope. And so again, I should have some kind of inflection point right here. It looks like it's going from concave down to concave up, so I did a fairly good job of that. I was actually paying attention to it as I went. So, you know, we ended up with a fairly good look at what the graph looks like. Now, just one final check. The slope of my first derivative graph is positive here. Now the slope of the first derivative is the second derivative. And so that means this should be a positive second derivative. A positive second derivative should be concave up for my original function. Note that it's concave up there. After this point, from this inflection point to that inflection point, I've got a negative slope, right? It's varying degrees, but a negative slope everywhere between here and here, which means a negative slope should mean a negative second derivative, and therefore concave down for my original function. And then after this point, again, I'm back to a positive slope. A positive slope means a positive second derivative, and therefore a concave up for my original function. And so there we've put everything together, and we've created one possible f of x. Now, this could be flexible. It could shift up or down. A graph that looks something like this, right, with stationary points have to be at the same x values. Okay, but something like this, oops, there we go, would be just as acceptable because I got a stationary point at the right places, stationary point, stationary point. I've got inflections at approximately the right places, okay, and the concavities all match up. So note that it could be anywhere in up or down, but these special points, the stationary points, the inflections, concavities, should all match regardless of how high or low you actually draw your graph. Okay? And that's it for today. All done.